Imagine a light beam leaving point A to reach point B. We'll expect it to take the simplest, straightest path. But in quantum physics, light doesn't do just that. It tries out every possible path, no matter how crazy, zigzags, loops, even path to the moon and back, before it gets to point B. Sounds wild, right? But that's the core idea of Feynman's path integral. We'll explore why the strange idea is actually true, using simple examples without complicated math. Let's look at the famous double-slit experiment. We fire one photon at a time at a wall with two slits. Behind it is a screen that shows where the photons landed. Over time, the dots on the screen create a pattern of light and dark bands. This is an interference pattern, which can only happen with waves. This happens because a photon isn't a tiny ball traveling one path. Before it's measured, it's a wave of probability, and the interference comes from this wave passing through both slits at the same time. To figure out where a photon might land on the screen, we add up the probability waves from both slits. Then we square the result to get the actual chance of finding the photon at that spot. What if we add a third slit? Then we just add a third wave. More slits, more paths. Feynman pushed this further. What if we have infinite slits and infinite barriers so that the barrier effectively disappears? The path integral says that in order to find the probability of reaching point B, we sum over every possible path. Therefore, even in empty space, a photon must consider every possible path because there are infinite slits and infinite paths that we need to consider. So why do we only see the simplest path? It's because of a fundamental quantity called action. Imagine each path has its own little clock. The direction that the clock hand points to depends on the action. Path with a lot of action points so randomly that they cancel out when they are added together, and path next to path of least action points in the same direction. When added together, they will form one strong hand that dominates all the other paths. In other words, light does travel to the moon and back, we just don't see it because that path is cancelled out.